Okay, class, today we're going to be looking at different kinds of chemical reactions and learning how to classify them so that way when you see chemical reactions in class or in lab, you'll know exactly which category they belong to, and that can give you information on how the reaction would proceed, and eventually you can even predict products of reactions and feel like a chemical genius. Okay, the first thing that I want to point out before we proceed is that for all types of chemical reactions we'll see in this PowerPoint, you'll notice that in the title I give you the name of the reaction type, and then in orange next to it in smaller letters I've got something written, and that will vary depending on which type of reaction we're looking at. What I did for this orange part is kind of give you an indicator. This is something that you can use when looking at any chemical reaction to identify exactly what kind it is. Okay, so the first kind we're going to look at is synthesis reactions, and you'll notice that the indicator, the ding ding ding, is actually that all synthesis reactions produce one product. Synthesis reactions generally have the form A plus B yields AB. Now I want to go ahead and kind of emphasize the fact that when we write it as A plus B yields AB, that does not necessarily mean that you only begin with two reactants. The big key is that you only have one product. So you can have as many reactants as necessary. As long as they produce one product, you have a synthesis reaction. And these synthesis reactions can occur in many different ways. You can have two elements, like in this example, we've got sodium and chlorine producing sodium chloride. So that's two elements as reactants producing one product. That's synthesis. You can also have two compounds, such as this calcium oxide and water, producing calcium hydroxide. Again, just one product. Okay, and then you could even have one compound and one element. And remember, oxygen is diatomic, just like chlorine is why it exists as O2 in nature. Again, in this compound and element synthesis reaction, we produce just one product. So again, one product, always synthesis. The second kind of chemical reaction that we'll look at is a combustion reaction. You'll notice up here in the title I've got combustion reactions, and the dinger is that it always has O2 gas as a reactant. Okay, you can have anything else, but as long as oxygen is a reactant by itself, as far as like elementally by itself, you have a combustion reaction. We can have a combustion reaction occur between a metal and oxygen, a nonmetal and oxygen, or a hydrocarbon and oxygen. You'll notice in each case, O2 gas is a reactant. We'll produce different kinds of products depending on which type of element, metal, nonmetal, or compound, which hydrocarbon you're dealing with. You'll produce different products. Okay. Now you'll notice in the metal and non-metal combustion reactions, each of those produce only one product, either a metal oxide or a non-metal oxide. So these two types of combustion reactions are also synthesis reactions because they produce one product. The third type, for the hydrocarbon, you'll generally produce carbon dioxide and water, but again, since that's more than one product, this type C basically is also not a synthesis reaction. So first two are, the third is basically just a combustion reaction. Okay, I've got examples here. We've got iron, that for our metal and non-metal, producing a synthesis reaction, and also we've got a metal and oxygen for a combustion reaction. In both cases, the same reaction occurs to produce the same product, iron 3 oxide, that's metal oxide. If we look at carbon and oxygen, we've got a non-metal reacting with oxygen, or you could even just take two elements to produce the one product, carbon dioxide. In this case, this is both synthesis and combustion. Synthesis because of one product, combustion because of the O2 gas. You can look at the combustion of methane, and the combustion of methane is a hydrocarbon, so we should produce carbon dioxide and water. But again, we've got O2 gas making this a combustion reaction, and we do not produce one product, we produce two products in this reaction, so this is not synthesis. The third type of chemical reaction we're going to look at is something called a decomposition reaction. And the way that I like to think about decomposition is that it's the opposite of synthesis. So instead of one product, you have one reactant. So synthesis reactions, you put stuff together to synthesize something, and decomposition, you have one reactant that is decomposing or breaking apart. So we see the form AB yields A plus B, or as many different products as necessary. Again, you only need to have one reactant for it to be categorized as a decomp reaction. Some examples here, we can have ammonium nitrate. And ammonium nitrate will decompose to form dinitrogen monoxide and water. You could also have sodium nitride that as it decomposes, it will break down into the elements sodium and nitrogen. All right, so the fourth kind of chemical reaction that we're going to see is something called a single replacement reaction. And this is a little bit more complicated than the first three types, synthesis, combustion, and decomposition. You'll see up here, I've got an element plus a compound making an element and a compound. And that's kind of vague, but it is a good kind of skeleton to look at. It kind of helps you really observe the chemical reaction as a single replacement reaction simply by looking at the reaction equation. Okay, but to talk a little bit more about what this means is that you have something like some element, and we'll call it element A. This can either be a metal or a nonmetal, reacting with a compound where you've got, let's say, BX, where A and B are the same type of element. So either both metals, or you'll see something where BX and A and X are both nonmetals. The only exception is that if you have a metal for A, that B could also be hydrogen, and that's going to depend on the metal's placement in something called the activity series. But my way of thinking about this, and I think that most people will teach it this way, is that this element, depending on its strength, can kick out the similar element in the compound to produce a new compound containing the original element, and then the element that is left is now the element that was kicked out of the compound. I know that seems kind of weird, but basically if A is strong enough, it can kick B out to form a new compound and leave B alone. You can think about it like dating, and if you've got a big, buff, strong guy, he might be able to win the girl and leave the former boyfriend all alone. But we'll just pretend that that doesn't happen in real life. All right, again, you need the activity series to predict how that reaction is going to proceed, because the activity series that's on the back of your periodic table, the green periodic table in class, that activity series does list the strengths of different metals and the strengths of different nonmetals to help you predict whether this reaction type would occur. All right, so let's look at some more examples. So in this example, no, actually we got two. We're going to look at this first example here. I've got lithium, which is a metal that's all by itself. And then if I look at my compound, I've got water. Now again, I don't have another metal here and it has to be similar. But again, hydrogen can react with any other element or ion, similarly to different metals, especially metals in group 1 like lithium. So here, if I look at the activity series, I can see, which you'll have to see on the back of your periodic table, but I can see that lithium is higher up on the table than hydrogen is, or in your chart, depending on which version you have. Okay, so since lithium is higher up, meaning it is more reactive than hydrogen, lithium's going to kick hydrogen out. So I've got now hydrogen in its elemental state, and it will react with the hydroxide, which was part of water. So now I've got lithium hydroxide as my new compound, and hydrogen gas, which is just elemental hydrogen, hanging out to the side. The other reaction I have deals with a metal replacing another metal. So I can have copper that's all by itself, and this is a reaction you'll see in lab. But copper all by itself, copper is more reactive or higher up on the activity series than silver, which means it is strong enough to kick silver out of this nitrate compound. So now you've got elemental silver all alone in your reactant side, or product side, excuse me. And then copper is now going to bond with nitrate, and we're going to form copper 2 nitrate, and that's going to be in solution. You'll actually see this reaction again, and it is super, super, super cool. Okay, again, still talking about single replacement. Remember that your activity series does order these metals by reactivity with other metals or also with hydrogen. That's how, again, you'll predict whether or not a certain reaction will occur. An example of that is, again, I'm going to refer to this copper reacting with silver nitrate. Because copper is higher up on your on your activity series on the back of your periodic table, it will produce the reaction where silver is kicked out and now copper is in a compound with nitrate. But if we were to have reversed the reaction and had silver as the metal by itself and copper in the compound with nitrate, silver is lower than copper, it's below copper, meaning it is not as reactive as copper. So silver is not strong enough to kick copper out of the nitrate compound, and since it can't create a new compound, no reaction would occur. So instead of predicting products as we did in the example above, you would just put in R or no reaction. And sulfuric acid or hydrogen sulfate, you would first want to write out their chemical formulas with their states as aqueous and a little plus sign in the middle to show that you're beginning your skeleton equation. Okay. The next step is to identify your cations and anions from each compound. So we're going to take our first compound, aluminum nitrate, and we know that our cation would be Al3+ or aluminum ion, and our anion would be the nitrate anion, so NO3 1-. If I look at hydrogen sulfate or sulfuric acid, I see that my cation is H with a positive charge, or the hydrogen ion, and that my anion is sulfate, or SO4 2-. The next step is to pair each cation with each anion from the other compound. So here I've got Al3+, that is going to pair with SO4 2-. So I'm going to take aluminum and sulfate and form a new compound, and then I'll take my hydrogen and nitrate and form a new compound. And then after that, we're going to have to swap and drop to be able to find our formulas for the next set of compounds for our products. Okay, remember the whole point is to balance charges. So we see that the 2 from sulfate drops down after aluminum, and the 3 from aluminum drops down after sulfate. So I get Al2SO4 3. If I look at hydrogen and nitrate, they both have a 1 charge, so a 1+ or a 1-, and those cancel out, so we get HNO3. This is actually nitric acid. After that, you're going to use the solubility rules that are on the back of your periodic table next to your activity series to predict the states for each element, each of the compounds. So if I look at the solubility rules on the back of my periodic table, I see that there's not really a rule about aluminum, but there is a rule about sulfates that says that most sulfates are soluble. So because it's soluble, that means it dissolves in water, and I'm going to put AQ. All right. Then I can look at HNO3, and I actually see that there's another rule that talks about nitrates, saying that most nitrates are also soluble. So I know that HNO3 will be aqueous because it dissolves in water. Generally, both of these will not have the same state of matter. Most of the time, you'll have one thing that's aqueous and something else. Your other species will be solid, or it will be liquid water. Once you have found the formulas and the states for your products that you have predicted, then you can add them to your skeletal equation to complete the equation, and then just balance it, just like we've done in class. So these guidelines here should help you predict products and write and balance a perfect chemical equation for a double replacement reaction. All right, now that we are done covering the types of chemical reactions, you'll get plenty of practice in class. To go ahead and prepare you for that, I would like for you to complete the homework problems that I've assigned in Canvas in the homework section of your folder, and then we will begin class with a quick little warm-up and then do many, many, many practice problems together. Okay, I hope to see you tomorrow.